Hello everyone. Today we are going to explore one of the most exciting chapters in chemistry, atomic structure and radioactivity. Now I know what you're thinking. Atoms, particles, radiation sounds complex, right? Don't worry. I'll break it down step by step, and by the end of this class, you'll be amazed at how much you understand. Let's begin with a simple question. What is everything around us made of? Yes, it's matter. And all matter is made of atoms, the smallest unit of an element that still keeps its chemical identity. Now, each atom is made up of three subatomic particles, electrons tiny, negatively charged, and constantly buzzing around the nucleus, protons positively charged, sitting in the nucleus, neutrons neutral particles. Also in the nucleus, these tiny players create the vast diversity of matter we see. 2. Let's compare them. Here's how they differ. Electrons are super light and found orbiting outside the nucleus. Protons and neutrons are much heavier and live inside the nucleus. And fun fact, a proton is almost 2000 times heavier than an electron. Alright, two important numbers to know. Atomic number, Z, tells us the number of protons in an atom. If Z changes, the element changes. So it's the element's ID. Mass number, A, is the total number of protons and neutrons. Think of it like the weight of the atom's nucleus. So, mass number is equal to protons plus neutrons. Easy. Let's untangle these isotopes, same element, different mass. Like hydrogen, deuterium, and tritium, all have one proton but different neutrons. Isobars, same mass number but different elements. Example, carbon 14 and nitrogen 14. Isotones, same number of neutrons, different everything else. Example, carbon 14 and nitrogen 15, both have 8 neutrons. I know the names sound alike, but now you know how to tell them apart. Thomson's model, imagine a watermelon. The red pulp is positive charge and seeds are electrons. But it didn't explain the atom's structure well. Rutherford's model, he fired alpha particles at gold foil and found that most passed through, but some bounced back. That told us atoms are mostly empty space with a dense core, the nucleus. Bohr's model, he added structure, electrons revolve in fixed energy levels or orbits. They can jump between levels by gaining or losing energy. This model explained why hydrogen emits light in specific colors. Pretty cool, right? The nucleus is tiny, about 1 femtometer in size, that's 10 superscript 1 meters. It holds protons and neutrons together with something called the strong nuclear force, the strongest force in nature. You've probably seen symbols like superscript 1c. This tells us atomic number Z is equal to 6 protons, mass number A is equal to 14, so it has 8 neutrons. This shorthand helps chemists understand atoms at a glance. Here comes the thrilling part. Radioactivity is when an unstable nucleus spontaneously breaks down, releasing energy and particles. It was discovered by Henry Becquerel and further explored by Marie and Pierre Curie. Their work literally changed science and medicine forever. The three types of radiation, let's break them down. Alpha particles, to protons plus to neutrons, like a helium nucleus. Heavy, slow, and easily blocked by paper. Beta particles, high energy electrons or positrons. Lighter, faster, and more penetrating. Gamma rays, pure energy, like X-rays but stronger. No mass, no charge, but very penetrating. Each has different effects, uses, and dangers. Radiation, charge, mass, penetration, ionization, alpha plus to heavy, low, high, beta, 1 plus 1, light, medium, gamma, 0, very high, low. So, gamma rays pass through walls, but alpha particles can't get through your skin. Radioactive atoms decay over time. But here's the catch: we can't predict which atom will decay, only how many will decay over time. The law is Nt is equal to N times E, lambda T. This tells us how many atoms are left at any time. Decay constant, lambda, is just the rate at which a substance decays. Half-life, T half, is the time it takes for half the sample to decay. Example, if a substance has a 5-year half-life, after 10 years, only 25% remains. Mean life is the average lifetime before decay. 1 divided by lambda. Each radioactive substance has its own unique half-life. Unstable nuclei don't always become stable in one step. They go through a series of changes called a decay chain until a stable nucleus is formed. Example, uranium-238 eventually becomes lead-206, passing through several alpha and beta emissions. Fission, a big nucleus splits into two smaller ones, releasing energy and more neutrons. This is what happens in nuclear reactors and atomic bombs. B. Fusion, two light nuclei combine into one heavier nucleus. This powers the sun and stars, and it releases immense energy. Einstein's famous equation tells us energy is equal to mass times speed of light. Superscript 2. Even a tiny loss of mass releases a huge amount of energy in nuclear reactions. This is how we change one element into another by bombarding it with particles. It was first done in 1919 by Ernest Rutherford. He changed nitrogen into oxygen. That's modern alchemy. Let's talk about how we use radioactivity, medicine, cancer treatment, diagnostic scans using isotopes, agriculture, food sterilization, creating better crop varieties, archaeology, carbon-14 dating of fossils industry, detecting leaks, studying metal structures. But yes, radioactivity isn't always our friend. Exposure to radiation can damage DNA, cause cancer, and leave behind dangerous nuclear waste. So we use lead shielding protective suits, radiation counters to monitor levels. Always respect the power of radiation. Phew, that was a big chapter, but we've covered everything, from what's inside an atom to what powers the sun. Radioactivity is powerful, useful, and risky all at once. Understanding it helps us harness its benefits and protect ourselves from harm. In the next class, we'll solve some numerical problems based on half-life and decay rate. Until then, revise well and keep questioning the universe around you. Jai Hind!